So first of all, let me quickly introduce myself. My name is Frida Ullumbrøer. I'm a senior researcher in Centef, and I'll be chairing this session on batteries. So welcome everyone. I'm happy to see so many of you joining for the battery session. Hopefully we can give you some more insights on what we have been working on for the past 4 years. Quickly, this is the schedule for today. So I will give you a brief introduction to the battery key value chain from the TREASoURcE perspective. Then I will continue, just kind of slide into the next, since I'm giving both presentations, and tell you a little bit about the challenges and policy recommendations that we have been working on. Then my colleague, Jakob, will be talking about the battery demo units that we have set up in this project. Following, another one of my colleagues, Meron, will talk about the macroeconomic assessments that they have done. Then we will have a coffee break, then followed by Green Delta that will give you some insights into the sustainability assessments. Noman, where are you, Noman? There you are. Sorry, right in front of me. We'll give you some perspectives from Estonia. And then finally, we will have a panel discussion at the end. So that's the agenda for this session. And hopefully you will sit and feel like you've learned something after when we finish. So just to get right to it, the first part, just to kind of give you a little bit of overview and just of what this is about. So first of all, why are batteries important? We see that society is becoming more and more electrified. It's getting more and more, not just in the EVs or the electrified transportation, but we also see it in stationary storage and in a lot of places. And of course, everyone, you all have laptops and cell phones where batteries are, but those we've had around us for some time. But we see also there's changes in how the grid is built up. Where do we put in batteries to kind of stabilize the grid, to support the grid? Is it going to be centralized versus local energy production and so on? And we also see more and more intermittent energy sources being implemented into the grid, like wind and solar. So these are some predictions done by Bloomberg. And we see that this is how they predict the local or the global electricity production to evolve over the next 25 years. And we see that a significant amount of, no, not working on the screen, but a significant amount is going to be wind and solar by 2050. More than 50%, in fact. And those are intermittent sources, which means that they don't necessarily produce when we want them to produce. They produce when there's wind and when there's sun. So we need to have energy storage to make sure that we still have electricity when we need it. But we also see that solar and wind has become a lot cheaper. Batteries are becoming more affordable and better. And we also see stricter regulations and favorable incentives. Some of the areas that we will also see batteries in use is to support flexibility needs. We see the figure to the left here shows the hour-to-hour flexibility needs per region. The EU, China, and India. The blue numbers are 2021 numbers, and the green ones are the 2030 predictions. And you see that the flexibility needs are really increasing. And if you look at the scenarios, so the figure to the right shows how these flexibility needs are going to be covered. There's one that's for the advanced economies, the top one, and then there's emerging markets on the bottom. And then they have looked at different scenarios. It's the 2021, which is then taking into account the legislative landscape as of 2021. Then there's the steps and the APS, which are two slightly different scenarios. One is a more forward-looking, where they see that the legislation will favor more green solutions. The other is more kind of status quo, not much changes. But either way, we see, regardless of the scenarios, batteries, as we see in the purple here, will be a significant part of the solution. So even if we don't have much policy changes, we will still see a lot of batteries. We also look at some global BESS. Here is the battery energy storage system. Capacity predictions from McKinsey. On the top here, which I've circled in the green box, shows the actual energy capacity in gigawatt hours. And then this columns shows what type of batteries. And the black part here is the utility batteries, which are the really big batteries, the large ones. And we see that the numbers here are increasing. And these numbers are even a little bit old, in a sense. They're from 2023. So the predictions are even increasing even more. So batteries is part of our future. But there's also a lack of resources. If we're going to have all new lithium-ion batteries into this, we are going to run into shortage of materials. So recycling, reuse, life-extending measures is going to be an important part of the solution. The figure here shows the circular EV battery value chain, where you see the little circle at the bottom shows how we can take batteries out from the car, batteries that are still usable, and put them into other applications, such as stationary storage, before they are eventually sent to recycling. Hopefully that can extend the battery lifetime by anywhere from, let's say, 5 to 15 years, depending on how the batteries are used in their second life. So, yes, I'm on time. Over to the challenges in policy. So this was one of the first things that we did in the TREASoURcE project for this work package. We started to look into the regulatory landscape to see how easy is it to get this market to grow. What are the challenges? And can we actually recommend some changes which can potentially accelerate this market? And so we split the challenges into some categories. Technical challenges, then we looked at the regulations and legislation. One that we've called eco-design, and then safety and reliability. And of course, the cost is kind of this overarching that affects all of these categories. Now, we have a report that's published on this. We also have a scientific publication, which you're free to have a look at later. Those are both on our website, so you can find them there. So this is a very, very short summary of what we found. And we identified a total of 10 different main challenges. So for the regulations and legislation, we see that there's a lack of regulatory environment, testing, and safety standards for repurposing of electric vehicle batteries. We also see that after going thoroughly through the EU battery regulation, which came in 2023, it really favors battery recycling. There's quite strict and set targets for recycling, which I've indicated here, some of them in the table below. So one thing is that you have targets for collection of batteries and so on, but also there's targets for minimum recovered content in your batteries, and also recovery targets for waste batteries. But then you also have by 2030 or 31, there will also be a minimum amount of recycled content required in new batteries. And what we are afraid is that this could go at the expense of second life and life extending measures, because you will need to recycle the batteries faster. They need to go into recycling to kind of have enough recycled materials. So that is a real a challenge that we see could potentially come. Excuse me. Now over to the technical challenges, and there's a number of these. Here's a bit of a summary. So one thing is that right now there's a lot of historical data stored in the battery management system in the BMS. It's not necessarily accessible to the second life stakeholders, which makes it much more difficult to know how you can reuse a battery, because you don't necessarily know the state of degradation. You need to do a lot of extensive testing to figure that out. We also see that there's, even though we talk about lithium-ion batteries, within that umbrella, there's so many different chemistries. When I talk about chemistries, it's mostly changes in the cathode material, which you see in this figure here is referred to NCA, which is the nickel, cobalt, aluminium, LFP, lithium iron phosphate, NMC is the nickel, manganese, cobalt. And we see specifically that the LFP batteries are really increasing. In the Chinese market now, there's almost all LFP batteries for certain applications. And we also see an increase in the European market. But that in itself brings on a whole another set of challenges, that the battery technology evolves so quickly. Another one is that when you evaluate these batteries, you need to try to find out, so if you have a battery at what we call 80% state of health, meaning that 80% of the initial capacity is left in the battery. 82 batteries at 80% state of health might have degraded very differently. So on further use, one battery can maybe last for another 10 years, another one dies in 2 years, even if they are then originally at the same state of health. And batteries is kind of like a little black box and very challenging to know exactly how they have degraded without opening up the battery. But if you open it up, you destroy it. So there's a lot of challenges in this, and it's time consuming and costly. If you had access to a lot more of the historical data and information about the battery, this would have been a lot easier to figure out. Eco-design is another one. And here comes the fact that you have so many different car manufacturers. And even with the same car manufacturer, there's, for the same make and model, there could be differences in the battery system just within the same year it's been produced. You also have, there's a lot of glues, epoxies, and welding done, which makes the disassembly part of the battery very challenging. A lot of things is still done manually. You can't really automate a lot of these processes. And obviously, that adds cost. Then over to the safety and reliability. There's not, I mean, lithium-ion batteries in itself are relatively safe. There's really not a lot. If you look also at electric vehicles, there's not a lot of fires in electric vehicles, but you do hear about those that are. The challenge is that if there is a fire in the battery, it is really difficult to control and to extinguish. So that's, I think, why also a lot of people are more afraid of it. But this has also maybe created a bit more negative public perception of the batteries than what they kind of deserve. So that's one thing. Then reliability is, of course, a concern when you talk about second life, because, as I mentioned already, a battery down to about 80% state of health, you can predict relatively well through different modeling approaches how the battery will behave and how it will degrade depending on how the battery is used. But when it goes beyond a certain point, it becomes much more difficult to predict further behavior. And that's why also second life batteries will inherently be less reliable than a new battery. And that is certainly a challenge. We also have the end-of-life batteries that could be damaged. So before they can be reused in a second life purpose, they must be transported. In that transport process, batteries are considered hazardous goods. So there are quite very strict regulations for how you transport batteries. And also there could be things happening during the transport. So this is another thing that adds complexity and cost to the process. And again, the last one is the insufficient knowledge regarding design requirements for battery rooms. This is something that we've really seen in this project, that when you want to install a battery in a building, there's quite a lot of standards and regulations on the electrical system and how to connect it. But the room itself, what's the minimum requirements? How big must a room be? Where should it be located? What's the requirements for ventilation, for suppression systems, for detection systems? There's nothing on it, absolutely nothing. And that calls for a lot of challenges if you want to make sure that you implement this in a safe way. So, for our recommendations and solutions, again, I mentioned the EU battery regulation. We know that next year, in 2027, there will be the battery passport. The battery passport is going to be implemented gradually. I mean, it's going to be a passport, but the content of the passport will probably change over time and increase over time. Here are some of the points, like some of the main contents for now that will be included regarding raw materials, carbon footprint, chemical composition, use, and so on. It's also going to be graded access. So not all the information will be accessible to everyone. It's going to be on a need-to-know basis. But challenges here, it's going to take a long time before we have a significant amount of batteries on the market which do have a passport that can be used for second life. So we're still looking into 10 to 15 years before we have a significant amount of second life batteries with a passport. So the circularity also with the passport will hopefully change, but this is also still left to see. Hopefully it will lead to a more transparent value chain, enabling easier access to information, degree of, and of course this is something that we think will happen. It's left to see. Traceability will be easier, access to historical user data, and degree of recycling. And hopefully then cost will also decrease over time. Regarding the safety and accelerated uptake of second life BESS, and this isn't just for second life, we could also say that this is for batteries in general, BESS in general, but proper risk assessments, having good standards for that, how to handle a thermal event. A lot of people don't know. They could even do things if something happens. If they don't know how to react, what they do could even escalate the situation. Training of end users and operators. So we need a lot more knowledge to establish these guidelines. Another point, which is kind of my little thing here, like trading of new and used batteries. In Norway, we see people like selling used batteries just online on these online platforms to people who have no idea how to handle these. That could cause a lot of dangerous situations. Finally, eco-design, recycling, and reuse. Implementing quantitative targets for reuse of EV batteries. Providing incentives. Right now, new batteries are so cheap that it's really difficult for second life batteries to compete. More standardized solutions, I think, would help a lot. More clear guidelines on responsibility for collection and recycling, and more collaboration between end users, stakeholders, researchers, share information. I think that is really key. And finally, this is a policy brief that we just finished, thanks to also Kaisa here that designed all the nice things. That contains a lot of these points that I've just mentioned now. So this will also be published very shortly and will be on our websites. And here we have chosen to focus on the regulatory framework for battery rooms and the requirements for training, because that's a little bit of a low-hanging fruit that can be done more locally. And it's easier to do something about than, for instance, the eco-design. So that's why we've chosen to focus on that. Very quick summary. Battery market, it's changing so quickly on so many aspects. But we also see that demand for batteries is really just increasing. It's skyrocketing. The design solutions and differences here causes challenges. So that repurposing is more time-consuming and complex. And also, battery system installation best practices are not well established. So those are my, I would say, key takeaways from this part. Now, there's not much time for questions. We can maybe, yeah, you have one? Yeah, maybe here, just.
Hello. Far from being a battery expert, I've seen in China that they are standardizing batteries in EV, so you can drive in, swap in and out, so the charging is faster. So I wanted to know, because the EU regulated for the single universal charger for smartphones, etc., whether having a standard set of batteries for EV for other use would help the second life, or would it be something that would inhibit innovation in batteries? Because you mentioned like it's a quick changing landscape. So how do you solve this, or what would be the recommendations in terms of standards?
Yeah, very good question. So the charging, of course, is if you could just exchange the battery, that would maybe enforce more standardization, as you point to. And I think that at least in Norway, the charging facilities are so well established that a standardization procedure in those terms for personal vehicles, I think, would be difficult to implement. But for maybe larger, like trucks or other, like where you have bigger batteries that requires much longer to charge, could potentially be solutions for that. But it would certainly, if you had a standard solution like that, it would probably also help, especially with this eco design and more standardization of the design, for sure. But yeah, again, China is way ahead of us. All right. I spent more time on this than I had hoped, but we will have time to discuss also during the break, so feel free to come up and ask me questions, and I will be here the rest of the day. So now I will give the word to Jakob, who's been working on evaluating the economic part of these these battery systems. So, Jakob.
Thank you. Do people hear me well without the microphone, or should I be using the microphone? Yeah. Okay, so I'll be talking about the more economic part, the techno-economic part. I've also been doing quite a lot of modeling on this, and we'll show you some, how does the modeling theoretical potential of this battery compare to what was achieved on the 3 demonstration sites. So first, in general, what makes a good site for having a battery energy storage system? Next, I'll explain the 3 demo sites, which have been tested in TREASoURcE. And the last and biggest part would be the economic evaluation of these sites. So first, what makes a site good for BESS? Well, it needs to have several ways to make profit from a battery. So peak shaving is maybe the best known way to make profit from having a stationary battery. It is, if you have looked closely on your electricity bill, not maybe all private households, but most big places, they have this peak tariff, which is, what is the maximum amount of power you drew in any hour during the month, maybe even the year. And then you get a fee, which, is typically linear with the maximum peak. So if you can flatten out your electricity consumption, you get quite a lot lower electricity bill. And why do we have this peak shaving? Well, if people didn't care about using a lot of electricity in one single hour, the electricity grid would have a hard time. So the better, or like the flatter the electricity consumption from people, connected to the grid is, the more power the grid can, or the more energy the grid can deliver. And since a lot of people want to use electricity in the morning, people are taking a hot shower and turning on their kettles and stuff, the grid's adjusted. And by then doing peak shaving with batteries, for instance, the grid can work better. We don't need to build out new grid, or we can continue with the electrification. So doing peak shaving, it saves money, and it also helps society with the electrification in general. Next, we have a time shifting, which is also known as arbitrage sometimes. And then the idea would be that you have a battery, and you charge it when electricity is cheap, and you discharge the battery when electricity is expensive. And then typically, you discharge the battery to your own site. So if you're a building which uses some electricity for heating, you would then discharge the battery to the site in order to avoid buying electricity when the electricity is expensive. Time shifting also has a really good society effect, because when you can, if enough people do use batteries for time shifting, you would flatten out the electricity prices, and then, for instance, solar would be more profitable. Because now you see in Europe that when the sun is shining, electricity prices drop a lot, and that makes solar less economically viable. But if you have a flatter price, then solar and renewables would be more profitable, and you would get more building of solar and renewables. And then you have a solar support, which would be a kind of special case of time shifting, where solar support would be that instead of, if you have lots of rooftop solar, instead of selling it to the grid, you can use it yourself. And by using the solar yourself, you typically don't have to buy electricity from the grid. And when you buy the electricity from the grid, you have the taxes applied. And you don't get them when you sell solar to the grid. So solar makes the batteries extra valuable. We also have grid services like frequency stabilization and so on. You haven't really looked at that in these demo sites, but that is also a potential way to make revenue by just helping the grid have a stable frequency. Giving synthetic inertia and lots of different things there. And lastly, you might want to have battery energy storage systems in order to have backup power, or maybe you just want to have it for the using electricity when the carbon intensity in the grid is low and so on. So that was what makes a site good for battery energy storage systems. And now the demo sites. First, we have the Rudskogen race circuit. There they have employed this stationary battery, which is in a container. Like Frida mentioned, it's like you do have a battery room. How do you have the battery physically? And here they went for the container approach, which can make things simple. But then you need to have some electrical wiring and so on, connecting it to the site which uses the battery. And 120 kilowatt hour battery, is roughly 2 electric vehicles size of battery. And the maximum power is not so high compared to what you would typically use in a car battery, which is new. But that would correlate with, you don't want to use a second life battery too hard. So they limit the charging to 2 hours full charge discharge. Next, we have the Trosvik school. And here you can see that we have the rooftop solar. So then you can think that, oh, this might be a potential good place for solar support. And here the battery is stored inside the room. And this battery is slightly smaller than the previous one. And lastly, we have Lempele. Here it's this building which has a library and lots of different things. And there it is also a battery room where the battery installed, as you can see there. So that was the actual sites. And now I'll show you how do these sites actually, what do they look like from the economic perspective. And the Rudskogen race circuit. Here we see the electricity consumption of Rudskogen. And we have the summer in the yellow and the winter in the blue. And we see that there's a lot of peaks. The electricity consumption is fluctuating a lot. And you also see, it isn't any, it is always positive. We don't export electricity. It's only a consuming site. And if you look closer at the savings, just from peak shaving, we see the red ones here. That is the theoretical perfect peak shaving. And that would mean that you know exactly when the peaks happen and you shave them perfectly. In reality, you typically don't know exactly how big the peaks will be and when they will occur. So what we see is that the actually obtained savings from the battery installed are, in the best case, you are like 70, 80% close to the theoretical maximum. You've had some problems with the downtime, with the battery not doing its job because technical difficulties with a new second life battery. And also worth mentioning is that just the algorithm which controls the battery, and they got a new algorithm now this year. So we see that, the best month is the month with the new algorithm. Unfortunately, we didn't get to see more time than this, but probably the battery would be performing a lot better going ahead because you have like this learning phase. And I think this illustrates, as Frida said, that, repurposing a battery, doing this, it's a lot of novel work. It isn't, people haven't been doing this so much previously. So it takes some time to, find out how this works. Also, if we include the theoretical potential of doing time shifting, so now we have the blue part stacked on top, which would be the time shifting. We see that doing the perfect combination of time shifting and peak shaving would greatly increase how much money you can make on the battery. And the time shifting would typically be done every day. You would charge the battery every day when the peak, now the electricity prices are low, and discharge every day when they are high. So that does induce some more wear on the battery. So then it becomes a trade-off with, do you want to, maximize the savings, but also then wear down the battery faster. Peak shaving, you might not need to do every day. It might just be some days in the month which needs it. But the time shifting, it is, you would typically do it every day. But that depends. Maybe some days are very well suited for time shifting, others are not. So I think the key takeaway here, the battery can already do time shifting as well. You just need to change the algorithm in the battery. So I'll show you some figures later on the is this profitable or not. But with the obtained savings, there's a great room for improvement here. And I think, that is something which is nice to see. And then, just to show how time shifting potential for Rudskogen is. Here we see the dashed line being the electricity price throughout the day. And part of what makes this nice is that we have two peaks every day. We have the morning peak and the evening peak in the electricity price. And the battery would then charge in these red curves on average during the early morning hours or in the midday when there's a lot of solar power. And then it would discharge on these peaks. And then you have 2 times every day on average that the battery can make some profit from the time shifting. So this is just what, this time shifting actually would look like if it was implemented at Rudskogen. So TREASoURcE school, here we see there was some problems with the data from the site. We also see that we have not so many days, but a few days in the summer where they export electricity. And that says that, there is a small amount of possible solar support here, but not that many days. And also, a lot of July and August is missing, which is unfortunate. But looking here, we see that, the yellow here would be the theoretical potential for solar support. TREASoURcE also has fixed price agreement, so it is impossible to do time shifting because they have, this agreement which says the price should be fixed. We also see that the obtained savings are actually negative some days because TREASoURcE school had, it was hard to predict when the peaks would be. And the battery algorithm actually missed on the peaks and ended up making the peaks bigger. And this is, quite unfortunate with a lot of the way the electricity price system is. Instead of being more like, giving you savings in the electricity bill if you do well every day. It is like if you do one day wrong in 1 month, you can ruin the whole month's savings. So this is more like the way the electricity price system is made is not with the thought on making it easy for batteries to make money. But here again, a new algorithm in 2026, and we see that those months are the best. But you can also see that, TREASoURcE school seems more challenging than Rudskogen Motor Center. Then we have a Lempele, again, some data missing. Lempele has this very special way of calculating the peak tariffs. So then it is the highest peak of 2 months during 12 previous months. So there it is. If you do it, if you mess up with the way you charge and discharge the battery, then you have kind of ruined the next 12 months of potential savings. So this is a site which is incredibly, challenging. But here, they managed to operate the battery well. So Recube should have, kudos for managing to do that, because if they had done something wrong here, they might end up having, negative savings for 12 months and so on. So this is a site which is very challenging for peak shaving. But we see that, they have, especially last months there, done quite well. And then, the last and most important figure. Here we see the different sites. And here we have the savings per kilowatt hour of battery. So here we take into consideration that the batteries have different sizes. And you see that Lempele is like 1/5 of the profitability of Rudskogen. This illustrates how immensely important it is to find the right sites for employing repurposed batteries, or batteries in general. And we see also that the obtained savings, several months were missing. Some months actually ended up building the peaks instead of shaving the peaks. So there's a lot of potential for doing it better here. But especially if you look at Rudskogen, 700 NOK per kilowatt hour per year is a really good number. It would be around about 70 euros, because 10 NOK is 1 euro. And I would say that, if you want a new battery, turnkey ready, and you want it to be a payback time of roughly 10 years, it would be around this level. So Trosvik is slightly positive, but Rudskogen is, a quite good site. And this is without having the optimal size of the battery. So with this is just based on the period you saw around 2024, 2025. But for this period with the electricity prices, when you have the spot price and when you have Rudskogen's peaks, which are quite easily shaveable, you see that it is actually a good economic investment to buy a battery. But then the question is, do you want a second life battery or a new battery? As Frida mentioned, the new batteries, they are really wear resistant. You can charge them all the time and they don't degrade too much. But the second life EV batteries, which can be many years old technology, they are typically not that resilient. So I think, a key takeaway here, batteries, stationary storage, they can be profitable. You also have the nice thing with peak shaving, enabling the grid to handle more electricity, time shifting, enabling more flatter prices, which helps solar and other renewable sources. This is great that we see that this is profitable. But you need to improve the energy management system operating the battery. That has already been done. So this is, it would look way better if you just base it on the most recent algorithm. But then, the price of second life batteries versus new batteries, that is a key hurdle. So summary, choosing the right site is really important. There are many types of savings to be captured. The frequency saving also exists, but haven't been employed in this case. And this Lempele case with if you do something wrong, the whole year's savings will be destroyed, kind of. So hopefully electricity prices will become better so that peak shaving becomes easier. So we can get more resilient grids. And that was it.
Thank you. We have time for one or two quick questions, if there's anything. No, everything was crystal clear. Good. Great. Then our next speaker is also from Sintef. Seems like it's just all Sintef here. We should have also had Recube or /EcoStore here, but Axel is heavily recruiting for the next generation scientists, so he just became a father last week. That's why he's not here. And also Meron is stepping in for Moana, who is also expecting a baby. So we're really working on recruitment these days. But yeah, but Meron will tell us a bit about the economic assessments that Sintef has done for this this work. So please, floor is yours.
Thank you. This we have the presentation is based on this report. You can access it scanning this. It is the macroeconomic assessment of value chains for a second life battery markets. Frida already made all the backgrounds, how important it is. So we just want to see that what would be the economic implications of having the second life battery markets. And we took the case of Norway. And we focus here only their application in buildings in Norway. We use this economic modeling called input-output modeling technique. It's a very standard one to study impacts. We have built our own model called SUMS Norway, which is a family of just transitional assessment model. And we use it to assess short-term and medium-term effects of different policies, technologies, and the value chains. We have used this to many other projects, and the good thing about it is that it can be adaptable to other countries as well. And we have used it for 10 other countries so far. So what it does is that it is based on the baseline is a database that shows the macroeconomic performance of countries, like the interaction of different industries and products of the country. For example, for Norway, we used the 2022 data from Statistics Norway. This is all countries have this database, and it's used for calculating the gross domestic products. And this modeling technique is scenario-based in the sense that, so we have the baseline from 2022, then we ask, okay, then what would happen if we, for example, in this case, have repurposing of batteries compared to the baseline that where we don't have it. It is kind of dynamic because we can project the future. Here we projected up to 2040, and we get our results in terms of impacts, in terms of different, in terms of economic impact, that is gross domestic product, that shows the performance of the economy. In terms of job creation, for example, that shows how this introduction of this technology would affect society, and also in terms of emissions. I said it's scenario-based, so we base our scenarios based on different data. Firstly, we assume two pathways, like one social change pathway and another technological change pathway, and the social change based on other previous projects we were involved with. We got the data from there, and then the assumption in the social change pathway is like there will be a lot of behavioral and institutional change, which would result in lower energy demand and lower transportation demand in a way. But the technological change is more like there would be more technological progress. So there will be higher economic growth, and low battery costs are more deployment of clean technologies and so on. And based on this, we come up with these scenarios. Like we use the numbers from those pathways, and then we come up with the 3 scenarios. The first scenario is a baseline scenario. What is the status quo? What is now? That is, all used EV batteries are sent to recycling after first life, and all batteries used in buildings are first life. That is the current. Then we compare it with repurposing scenario, where we assume after first life, some of the EV battery, the share of EV batteries is diverted to repurposing for second life, and then they will be used in buildings. And but here, the total demand for these batteries will not be changed, but it will be the repurposing will only substitute the first life batteries. We also did some sensitivity analysis, because we assume different ranges for the repurposing rate, and we assume also, okay, what would be the acceptance rate? Like what would like different rates for the share of buildings willing to use second life batteries. All this will be shown in the results. Then one final assumptions for the scenarios. The scenarios are important because those are the basis for our analysis. So a new value chain, we introduced like this activities in the economy, like collection of used EV batteries. Like some of them were there, but they are not explicit in the economy, in the data. So we have collection of used EV batteries, battery repurposing, and battery recycling. And furthermore, we assume new first life batteries are imported. Like this is like Norway. So they come to Norway, and the repurposed batteries are supplied within Norway. And we also kept the recycling capacity to this, because I mean, after some years it would be because of the way the capacity is now. But like other activities like black mass and recovered metals, they are still exported. These are they are some of the assumptions that we have made. Then here are the results. So I'm going to show you like 4 slides with the results. The first one is the total economic impact of introducing battery collection, repurposing, and recycling in Norway. So here we have the social change pathway and the technological change pathway. So we have different numbers here. And for the purple is the baseline, and this one is full acceptance. I mean, this one is the baseline, this one's full acceptance, and this is very bad choice. The orange is limited acceptance. So we can see here that overall, the total economic impact in the battery industries, the 3 industries we introduced, plus the indirect spillover effects in the rest of the economy, by 2040 we can project it to be around 400 million euros. It's not really a big percentage of the Norwegian economy, but we can show that it can contribute positively. And also, if we want to see it, like how much the proportion is for the battery value chains, it would be like 35% of the contribution comes from here, and then the other 65% comes from the spillover effect. The spillover effect is that when we introduce these activities, they also interact with other activities, with other economic sectors, like the services, or they demand electricity, they demand transportation, they demand other services. So that effect that effect is about 65%. And we can see that technological change, rapid technological change brings more gains than the relatively than the social change, and also full acceptance gives more gains. The next one is comparing the repurposing scenario with the baseline. Here also we can see that repurposing increases GDP or like economy and employment, especially after 2032. Here you can see our projections up to 2040. And we see the effects are much stronger in the technological pathway than the social pathway. If you see, these numbers are more than these numbers. Limiting the size of the repurposing market, that is when there is less acceptance of the repurposing. Of course, we get smaller gains than when we get full acceptance. And we see that the recycling capacity, like we assumed, like we kept it it saturates in Norway, and then the excess is exported, and here we see even more gains after that, and also we see again that the emissions are increasing at the same time, but usually emissions increase with increasing economic activity, with increasing economy. So it's not necessarily, like we cannot say that it is necessarily because of the repurposing. Economic growth brings more emissions, like it's a known reality. And if we want to see the results closely by economic sectors, the impacts by economic sectors, we can see that the battery activities that we have brought contribute some here. For example, they contribute, okay, I haven't put any number. Like they contribute like 150 million kroners here, and by 2040, and they can employ around 200 people in Norway. And again, we see the other economic activities as well because of this introduction of this battery activities, that the other economies also gain, the other economic sectors also gain from this. And if we look at what the employment gains by education and skill groups, we see that mostly the largest increase is in the this one, those which are in upper secondary and vocational education, and not so much like university graduates are needed for this kind of job. And also in terms of skill groups, we see more technical and craft related skills are demanded more for this kind of activities than other activities. So to conclude, we see that increasing the second life use would generate some moderate positive impacts in the Norwegian economy. And these impacts extend beyond the battery-related activities through their indirect effects on the rest of the economy. And most employment gains are in the medium-skilled technical occupation. And repurposing can also delay the recycling activity, and it shifts recycling activity to later stages in the value chain. And but we have also some limitations in the model, that Exports of these end-of-life batteries and black mass, for example, are not fully included. The battery productions are also outside the system, as we showed you, as I showed you in the beginning. And some of the cost structures for the repurposed batteries may vary by scale, location, and time, but we used just fixed costs. And the data for Norway have been really we struggled really a lot here, and yeah, those are the limitations of our models. But otherwise, thanks, and then you can still access the the report here.
Yeah, thank you. We have time for some questions, if there's any questions. Anyone? Yeah? Wait, John? Yeah.
Thank you. So thanks a lot for the very nice presentations. I'm just wondering, because as far as I know, the input-output table, they do not have the columns for the battery or battery production or battery recycling. So then I'm wondering, how you convert those input-output table to this battery recycling case. Yeah, thank you.
Yeah, that's what I said. These are the new activities we have introduced into our models using different cost data, different estimations based on data from other projects, and based on these different pathways for EV battery availability and so on. So we used cost data from different sources and different assumptions to introduce them into the economy in terms of these three industries and products into that table. That's what you do, like you split them from other industries and so on. That's how normally you do it in this modeling.
Okay. Yeah. So for example, for Norway, so you get some bottom-up data from industries in Norway, and then you use some assumptions to convert those input-output table. Do I understand correctly?
Yeah, not necessarily from industries, but like from other. We get external data, cost data, to make this different assumptions, and then split them out. Like, for example, recycling exists, right? But it's not explicit in that table. So we took it out from based on assumptions. We took it out from the existing industries, but repurposing doesn't exist. So we introduce it like that, like using external data. Yeah.
Okay. Yeah. So yeah, another follow what you just mentioned. So because I'm located in Denmark, so I'm just wondering. So since you introduced the situation in Norway, and I'm wondering, if I want to use this model for the Danish case, what kind of things I can do, to,
Yeah, we can also talk later, but you can, as I said, all countries have the input-output table, right? Yes. So you start from there, and then you have to come up with the external data to help you split the industries and so on. But your starting point should be like to get the input-output table for Denmark, which is definitely available. Yeah, that's your baseline.
Okay. Yeah, thank you.
You're welcome.
Okay, thank you very much. Any last questions? Yes, then Kato.
Thank you. Is it possible to say more concrete about the investment and income at the Rudskogen case in the pilot period, payback time, for instance?
I guess that question goes more to Jakob. Yeah, we can take that.
So you said more about the payback time for the pilot versus the... Yeah. So it depends a lot on what the cost actually was. So, and I don't have access to what the cost was. But I think if we have like a good case that you have, yeah, you buy the battery system and yeah, you buy it brand new. It is no complications. It is easy to install. You've done it before. You know how to do it. Then I would say that the payback time could be maybe slightly below 5 years, but it depends a lot on the electricity prices. We have seen some years with very high electricity prices now. We have seen years with more normal prices. It also depends on if the peaks continue to be so easily shavable. But the way it looks now, I would say, yeah, but that is, yeah, the battery prices can vary by a factor of 3 maybe. But yeah, 5 years is my gut feeling if things go well. And especially if you also include the time shifting with peak shaving only, I think still 10 years should be doable.
All right. Since we now have a break next in our program, I think we can continue also some discussions there. But again, thanks to both Meron and Jakob and the presentation so far. And then we'll take 15 minutes. We'll meet again. We'll start up again at 2:15. So thank you, everyone. Okay, it's time to start back up. Our next presentation will be from Green Delta, Thomas, on the sustainability assessment. So please, floor is yours, and you click forward.
Okay, so thank you very much. So we have been talking about different aspects of the repurposed batteries. And of course, from the circular economy perspective, it's great to repurpose batteries, but what about the actual impacts that repurposing has? To answer that, we need to conduct a sustainability assessment, which I will now briefly present in the next 10 minutes. So for the sustainability assessment that we performed, it's actually composed of two different types of assessment. For the first part, we looked into the demo sites, the methodology of lifecycle sustainability assessment, looking into all processes that happen within the life cycle of the repurposed battery systems. But then, since TREASoURcE is also a project that aims to bring the change on the territorial and regional scale, we also conducted a regional assessment where we combined this lifecycle sustainability assessment approach with system dynamics, where we were able to get more of the systemic aspects into the assessment and also look into, for example, material flows. So generally, the system dynamics approach is basically a methodology to represent the system by the collection of stocks, flows, and variables that together comprise a specific causal structure that then allows you to simulate how the system will behave over the course of time. And we combine this with LCA conducted in the OpenLCA software to kind of get the sustainability assessment with the contextualized view of the system. So for this first type of assessment, for the demo sites, we were looking into the 3 sites as Jakob has presented. So these are sites in Norway, in basically southeast Norway, Rudskogen, Trosvik, and then in Finland, in Lempäälä. And here the scope is basically to understand what is the sustainability from the point of view of the installation operator. For the regional assessment, we are looking into the region of Greater Oslo, Stor Oslo. And here the aim is basically to understand what would be the implication of repurposing on the scale of the region, informing decisions, for example, for municipalities or policymakers. And we were looking into 4 different battery chemistries, NCA, NMC, LFP, and LMO. And maybe what's important to mention is that this simulation was done for the next 45 years, so between the years 2025 and 2070. So here are the results for the demo site assessment. I'm not sure if you can clearly see all the legends, but what's important here to notice is the consistent reduction of impacts for the repurposed systems compared with the first life systems. So the repurposed systems are represented by the orange and green bars, while the first life systems are represented by these purple and yellow bars. And as you can see across all of these impact categories, the repurposed systems actually provide some environmental benefit. But what is important to consider here is how we account for the first life of these EV batteries that are then repurposed, because the results I'm presenting here actually assume that all of the environmental impacts associated with the first life of the EV batteries are allocated to these EV batteries. So the impacts we see here for the repurposed systems are only the impacts that occur from the point of collection of these EV batteries. But we also perform some sensitivity analysis to, for example, allocate 50% of the impacts of the first life to the repurposed systems. And we still saw that there was a decrease in the impacts for the repurposed systems compared with the first life systems. Here we are just looking into the composition of the impacts, looking into the climate change impacts. And we can see that there's really a big difference between the repurposing impacts represented here by this slightly paler purple compared with this darker purple, which is the first life production. And what basically differentiates the sites is the energy that is being lost during the usage, because this comes from a different grid. So that's what basically represents the differences between these two sites. And as you also can see, there is a certain fraction of the impacts that are actually negative, meaning that these would be environmentally positive, so prevented impacts, and these come from the recycling. Now going into the regional assessment, we were able to model how would the different material flows develop over time. Here, what I'm presenting is the total capacity of the stationary BESS over the course of 40 years for two scenarios, the status quo, and then a scenario where there would be a 10-fold increase in repurposing capacity. And as you can see, the main difference actually comes from this blue area, which represents second life LFP batteries. And what's maybe interesting to notice is that these two areas at the bottom, which represent the first life stationary batteries, actually don't change among these two scenarios. So according to the causal structure that we have modeled, the second life batteries don't really substitute for the first life, but the increased capacity actually leads to increased demand and use of more batteries as a result. Here again, some charts on the material flows. So here we are looking into how the EV NMC batteries are actually treated, looking into recycling versus repurposing, and what happens when there is a mandated increase of reuse rate. And as you can see, and as it's probably not so surprising, when there is higher reuse rate, less of the EV batteries got recycled and more are repurposed. But what's interesting here is that there is also a more consistent tendency in repurposing compared with the baseline scenario. And now I'll just go briefly talk about the environmental impacts. Here we are looking into the accumulated carbon footprint for the two chemistries, NMC and LFP, and we are looking into the overall impacts that these two value chains are associated with. And as I hope you can see, most of the impacts are actually coming from the EV batteries. These are the dark purple areas here in these two charts, while comparatively smaller impact is actually originating from the stationary systems, which is this lighter purple. And in the case of the NMC batteries, you can see that there is this quite big area in the negative values, which again represents this credit associated with the recycling of the batteries. In the case of LFP, we found that the amount or the credits that can be granted to the recycling of LFP batteries are much smaller compared with the NMC. And here we are looking into the results for the stationary systems alone. So we isolated the stationary systems from the overall value chains. And as you can see here, the accumulated carbon footprint would then be dominated actually by the first life LFP, which is the yellow area here, while the second life is contributing much less compared with the first life stationary systems to the carbon footprint. And here we are looking into how much carbon footprint is actually created, or how much emissions, greenhouse gas emissions are released per kilowatt hours of electricity that is stored. And as you can see, there is tendency to decrease, which is explained by basically more energy being stored in these batteries as they are in stock. And here what we see, and what's maybe a bit surprising, is that the NMC batteries actually perform better than LFP, but this is caused, again, if we would go back to this slide, by this huge difference in the credits associated with recycling. And then we were also able to run some scenarios. Here we are looking into scenarios for increased repurposing capacity and then mandated reuse, which is a scenario where 50% of all batteries would undergo repurposing. And as you can see, actually, these scenarios that support higher repurposing actually result in higher carbon footprint. But this is again caused by the higher total stock of repurposed batteries that will be in the system. So if we would again then look into what is the carbon footprint per energy that's delivered from these systems, we would see that the scenarios that support higher repurposing, especially when there is mandated reuse, actually lead to decrease of the carbon footprint. But for NMC chemistry, this is much more prevalent compared with LFP. So to conclude, we saw that repurposing actually delivers environmental benefits in terms of all impact categories that we have looked into being reduced. Also, we can expect that the overall impacts of the BESS systems will decrease over time as the energy becomes more greener. And we also saw that the impacts, if we look at it from the overall value chain perspective, are actually driven by the EV batteries. And if we look into the opportunities, we saw that the mandated reuse scenario actually led to the increased battery use, which caused the overall carbon footprint to be higher. But if we look into this indicator that looks at what is the cost per energy delivered, we saw that this actually led to reduction. So the final takeaway would be that yes, there are environmental impacts when you use these battery systems, and even if these are repurposed, there will still be some environmental impacts, and therefore it's always important to consider these costs when you are thinking about, for example, supporting higher adoption of these systems. And in that context, I think it's quite useful to then combine this with the analysis that Jakob presented about the benefits that this system can deliver. So that's it. Thank you. I don't know if there is some time for the questions.
Thank you. Yeah, we have time for one quick question.
So if there is any question.
Could you say a bit about the CO2 intensity for the electricity when you charge and discharge the battery? Was it like one fixed, because you have like some energy lost due to the battery not being perfect? And yeah.
Yeah, so I basically used the fixed composition of the energy grid because I did some analysis and found that overall on average there is not much of a difference in the composition in Norway, for example. And even in the peak hours, the grid was actually on average a bit cleaner than outside of it, because basically the peak, or like when the price is highest, more hydro storage is actually used to generate energy according to the analysis that I performed, but it was not granular to the level of each hour. So this was based on like aggregated data.
Thank you for your answer. And a small comment would be, that like in Germany and places which are not so clean as Norway, you would often have like this, yeah, daytime it is cleaner with the solar, and then you could have big effects from that. But I think, as you said, Norway is, yeah, pretty unique with all the hydroelectric there. But yeah, thanks for a nice presentation.
Yeah, thank you very much.
Thank you. Okay, we have one more presentation before we go into a panel debate at the end. And we have Noman Shabir from Tallinn University of Technology. So you can see, yeah, it's on, so you can use that. And here, bring forward and backwards.
Thank you very much. So I will talk about the repurposing of electric vehicle batteries, evaluating the transferability potential from the Nordics, especially to the Baltics perspective. As my previous colleagues have talked about a lot of details, so I won't go too much details about what's in second life EV batteries. Probably you all know that. So what I would like to say is that a new battery, it's easy to predict. We can predict like how it will behave and how it will go from like 100 to 80%. The interesting part comes after 80%. So when the second life starts, then it's not easy to predict. All the models, they don't work at all. And we still haven't designed those kind of models. It could work very well for a couple of years, but then one day, all of a sudden, it's zero. So we don't know what happened yet. So that's here the problem lies, but it also gives us some opportunity, and it's a very good business case, but still we can use it. It can work for like 5 years or 10 years even. So this is the basic criteria for the EV battery repurposing. So we use it for a EV first life as it's manufactured. So it can go for like 5 years, 10 years, depending on, again, the usability, how you use your electric vehicles. And then for the end of the automotive life, then it goes for repurposing or a second life. And then it's usually used for residential applications, commercial, grid balancing, peak savings, as it has been explained earlier. So the pros and cons, low cost, in today's scenario, that's not a very good way to say this, that second life would be a low cost, because the cost of the new batteries have been significantly reduced. So it's like quite comparable now. In some cases, it's even cheaper, the new batteries are. But still, it's a very good option for grid resilience, flexibility for renewable energy resources, as it has been explained, and of course, the circular economy. And it could create a new value chain, create some new business models. Negativity or the cons are here. The liability is still unclear. It's still difficult to get the insurance companies on board. And if you just say, okay, we have a second life battery in the building, they are like, oh, they can just increase the premium, or they will just say, okay, no, it's not our cup of tea, so we will not insure it. Then, of course, there are safety and fire risks associated with the installation of a second life battery, if we are particularly talking about installing inside a building. Outside, it's much more easier, safer, but inside the building, so we have to take into consideration a lot many things. Then, of course, we don't have the data and the traceability available at the moment. So from next year, when the passports will come into play, then we hope this situation will get better. And of course, there are some issues with the permits and the grid connections as well, if there is a second life battery involved there as well. So this is the repurposing value chain. So first, it's usually collected, then a diagnostic is performed. So here, the price increase. Usually, if it's a second life battery, then you just take it out of a EV. Then if it's a kind of like a waste product, so it cannot be used. So it's free, but the collection, the diagnostic, the logistic, the remanufacturing, that creates the additional charge or additional price, and this is added to the second life value, and this in results increase the overall price of a second life battery. And then of course it's deployed for any application. So the use case that works well, as it has been explained earlier, that we have these 3 pilot sites, demo sites there. So it's worked quite well for residential community application, where you can use for self-consumption or peak shaving or time shifting applications as well. It's good for commercial and industrial applications as well. very good for these demand response programming, PV smoothing, microgrids and critical loads, for example, resilience, or if you have some island-based operation modes, it can work quite well. And of course, it can work with the grid for congestion relief, and of course to decrease the load or balance the frequency of the grid as it's required. So these all applications which work quite well. So recommendations from Estonia, we did a study in Estonia, so we had a discussion, and then we had a focus group of different participants and different stakeholders from the Estonian market. For example, in Estonian Ministry of Climate and Energy were there, the Estonian Fire and Safety Rescue Board were there. Then there were some private companies who were using these batteries, not the second life batteries, but the first life batteries for some grid balancing operators, or for example, some aggregators were there. The Consumer Protection Board was also there. So we had a very nice kind of like a focus group and even individual interviews with all these participants. So the main questions that we asked were, when does a retired EV battery becomes waste or a product? So if you just want to discard an old battery, then it's a waste. So then in some cases in Estonia, you have to pay for the waste disposal. But if you consider it as a product, then you don't have to wait. Then it's like something valuable. You can use it. But then comes some legislative things like who will test this battery, that if it's fine to use in a second life application or not. So that's the first question. Then who is the responsible for the safety? So generally the party that install this battery for some particular applications, they are the responsible ones for that one. But still it's a little bit unclear in some of the national legislation. So in some cases it's the OEM who originally produced this battery. Sometimes it's the repurposer, sometimes it's the installer, or sometimes it's the operator. So that's why the insurance companies, they don't want to get into this kind of mess. They want clear answer, okay, this one is responsible, fine. So then there is a problem of what data must be shared. So right now we don't have battery passports. So different battery manufacturers, they give access to their data on like a very limited basis. Most of the time it's a no, but sometimes they can provide for some diagnostic or some incident reports as well. Then the question was what kind of permits or building requirements or fire codes we need to install second life batteries inside the buildings. Outside the buildings, it's a different story, but inside the building, it's a totally different story. So then the producer responsibility and take back obligations at the second life. What if something goes wrong? So what will happen then? Do we give some kind of warranty, or when will be the warranty? Because we don't know, there are no models yet. So these are the insights from the Estonian stakeholders. There is a general broad support for sustainability purposes for the EV batteries, but the readiness is not there. It's just like fragmented. Then, of course, the regulatory and the role ambiguity is still there. Again, who is the responsible one for that battery? The safety and the responsibility are the prime concerns. Then, of course, the second life battery data, who will store this data, who will gather this data, and who will have access to this data. And then, of course, we need some more education about batteries in general, because batteries unfortunately suffer from like, in general, I would say like EVs suffer from like a negative perspective. Even today morning, a couple of my colleagues were answering, both of them has EVs. Is it safe to drive? And I assured them it's quite safe to drive as compared to an internal combustion engine. So the training should be there. There is insufficient technical infrastructure, and of course the market potential. That's a very big one. Because for example, in Estonia, unfortunately, we still don't have very high EV demand. I think it's still less than 5% of EVs as the total mix of cars. So still the demand is not there. So the recommendations were that we need to develop a national regulatory framework for this, especially for the second life batteries governance. We need to develop some pilot sites or demo sites just to showcase that it works and it's fine and it's safe. Establish testing and refurbish capacity in Estonia. Right now, we don't have any specific battery testing facility or a lab there where we can test even the first life batteries or the second life batteries. in that say. And of course, we need to improve the awareness about all these topics to journal, audience, producer responsibility, ownership transfer, all these things. And then we need to adapt and adopt the Nordic practices and the EU standards in the Estonian market and of course in the Baltics markets. And then we need to educate the installer, inspector, and of course the emergency services, especially the emergency services because the EV fires are very different to like a regular fire. And then we need to promote the cross-border knowledge exchange and consortia as well. So what are the criteria for transferability? So we need to transfer the practices that works well in the Nordic countries to the Baltics. The main thing is we just don't need to copy the technology, but we also need to copy the process, role, and evidence. And the focus on what can be transferred quickly and what policy needs that are required to change in the long-term perspectives as well. So this table just summarizes all these approaches in regulatory for second life EV batteries. So here you can see the EU framework, the Estonian context, and what's the gap and the challenge there. So we are quite lacking in so many things here. So this is the transferability potential from the Nordic market to the Estonian market, starting from battery testing, battery data access, fire safety, repurposing facility, grid integration, and standards and certifications. One thing I would quickly highlight that the market potential is huge. We have a lot of people who are willing to do that, but unfortunately, still the market has not yet evolved. Because for example, in Nordic countries, I particularly know about Sweden that you can participate in these grid balancing services if you have an aggregator of like 100 kilowatt. But in the Baltics market, it's 1 megawatt, which is like still a very big number. And we don't have even that much battery capacities there. Nowadays, people are moving towards this, but the change is like quite slow. So this is the first criteria, regulative and institutional fit. So first we need to clarify what's a waste and what a product, and then we can define a clear pathway for the end of waste, or if it's like a product, it can be reused for some other application. Then we need to define what's the roles and responsibility. Is the repurposer responsible, or is the installer responsible, or the operator is responsible for these kind of any incident events. Then the permitting readiness, building fire and safety approvals and grid connections, and of course the fire safety board should be educated enough so they can take care of these kind of fires if something bad happens. And of course the grid companies should also be notified that it's a second life battery, so they also are on board. Then the market access, we need a very strong business case if we want to increase the potential market of second life EV batteries. Then the technical and safety transfer, as in this project, as they were saying that they have developed some kind of a framework or guidelines for the battery installation rooms that are inside the building, so that could be quite useful. Of course, we need some testing infrastructures, lab, where we can certify what's the actual state of health of the batteries, the methods, and some models that where we can anticipate the failure of the battery, or we can predict how the batteries will behave. Fire response readiness, the rescue board should be conducting some training, some site requirements, or some inspection if the batteries, particularly the second life batteries, are installed there. Then the grid and ICT integration. So if there is a second life battery, a large site installed there, so there should be some continuous monitoring or data sharing that everything is working fine or not. Then of course the supply chain, qualified integrators, spare parts, and recycling partners should also be there. So these are the key takeaways. Start with a pilot project, small. Just show people that this works. It's quite safe. It has a strong monitoring and a controlling system. And then this co-develop a national checklist for the regulators, rescue board, and all the industry. And then invest in testing and traceability of these second life batteries. So this is a proposed roadmap that we need to establish a task force first. Then in the next year, we need a pilot site. Then after that, of course, adopt this EV battery regulation and certification schemes. Then develop these testing labs for public-private partnership or with the university as long it's work. And then in 2030, there's some scale repurposing facility and local market update. So thank you very much.
Thank you, Noman. That was a lot in a short time. Impressed. Yes. One quick question. Or we'll also be able to hear more from you in the next final discussion panel. Yes. So I'll ask you to stay here. So are there any quick questions for Noman? No? Okay. Then I will also ask Stein Cato to come up, as well as Pirkko. So let's see. So now we're slightly behind schedule, but not too bad. So we're okay. We'll be back in time for the last plenary session. So now we have a small panel, which they will be able to question. It's, I'm going to try to pronounce your name, Pirkko Etelauho from Business Tampere in Finland. And of course, Noman, which you have already met from Taltech, and Stein Cato Røsnes from, you are, well, I called you administrator because I couldn't find a good translation of your Norwegian title. But you're in the county of Østfold, and you have been also involved in the battery demo site at Rudskogen, which we have heard here earlier today. So thank you for accepting to participate in this panel. And I think we've heard a lot of good and interesting things now from both an environmental perspective and economic perspectives, and which we can gain from implementing not just second life batteries, but batteries in general. So, but now we have from Finland, we have from Norway, and we have from Estonia. So it would be really interesting to hear a bit even more in depth your experiences and what can be kind of done from a local perspective. So sort of from your perspective, like nationally in your country or even in your region, are there specific incentives or barriers, like anything that kind of promotes or hinders the implementation of either BESS in general or second life BESS? So, Stein Cato? Yeah?
Thank you. First, I will say that to test the use of second life EV batteries, we selected Rudskogen Motor Center as our pilot site. They see that the share of electrical car in motorsport is increasing, and they will need battery capacity to charge these cars throughout a full race weekend. So, because the permanent power supply in the area is not enough to support the level of charging that will be required. So it's starting to contribute to the electrification of motorsport in Norway also. But from Østfold's perspective, we see potential for second life batteries, but also some very concrete regulatory and structural barriers that are slowing down development. In our region, the biggest barrier is the regulation, and grid tariffs are still designed for one-way power system, not for flexible solution like BESS. Or second life batteries. So incentives exist, but they are fragmented and often too weak to trigger real investment. The positive thing is that we are seeing growing political interest in energy storage in Norway.
Thank you. Very interesting. I will get to you, Noman, but I will ask you first, Pirkko, because we've also had a case in Finland, in Lempäälä, where obviously we saw from Jakob's presentation that wasn't necessarily the best case for a stationary battery. Can you say anything about if you have any other experiences in Finland in that regards?
Yes, so of course, like the Lempäälä case was not easy, easy to build up. Of course, there was a lot of differences when we were talking about the EcoStore coming from Norway and making the installation. That in Finland there were some tricky issues there due to some different regulations and principles in Norway and in Finland. And of course this was like a very new approach, I think, as in any of our cases, and putting this kind of an energy storage system in an existing building where we don't have yet like the approach or instructions how to do it. It takes a lot of time. But I think that all in all the experiences are very valuable for us, and they have also like taken this into account in Lempäälä when thinking of new buildings and how this could be like implemented, these kind of solutions there. So I think it has been a very good experience all in all to learn from that. And of course, like energy storage systems are needed if we think about also both from national and regional level. Of course, there's a lot of investments coming up in renewable energy, and we also need to make the systems resilient and flexible. We need the storage systems there, whether it's first life BESS or second life BESS. So they are definitely needed, and we have a lot of like big and medium-sized industrial players that are utilizing energy. They want to have also, of course, their own resilience and flexibility in their environment. So there's a lot of potential for these BESS systems, but talking about incentives, there is like not any direct ones, like getting money for this kind of installations, but then more on the market-driven approach. As I mentioned, the industry needs the solutions, and also they have like the energy efficiency strategies where these kind of systems play a key role. So that's more like a market-driven approach maybe in Finland.
Yeah, interesting, very interesting. So Noman, like now we've heard already a lot from the Estonian perspective, but what is your what in your opinion is like the biggest challenge in sort of accelerating either second life BESS or even BESS in general in Estonia?
Well, generally, I would again like emphasize that the batteries in general, they have like a perspective problem. So this needs to be rectified. Like people needs to be assured that this is quite safe. It's not like something bad is going to happen. Because generally you see sometimes, like for example, a battery just exploded in a phone or some like battery bank. It could happen because of bad charger or like overcharger, which is like mostly 90% of the cases. But then it's like a very big news. And similarly, like millions of cars are working fine. Nothing will happen. But if something bad happens, then it's like a very big news. Yeah. So generally, battery storage is like, it has a perspective problem. Yeah. So people need to see it like in a different way. So these kind of like demo sites or small scale, they really help. It can assure people that it's working fine, it's relatively safe. So even in Estonian market, now people are beginning to explore these possibilities. There are no direct incentives, but generally for renewable energy services. And sometimes in summer, even last year, we had lots of negative prices. So that's where the batteries could come play. And then, for example, in evening time, the prices were like again shoot up. Yeah. So there it will go further.
Yeah, because it's really interesting this with the public perception. Because I think, well, you said you don't have very much EVs in Estonia, right? Yeah. Whereas in Norway, we are now almost selling only electric vehicles. People are hardly buying diesel or gasoline-driven cars anymore for private use. So we have something like 700,000 EVs on the roads in Norway, I think. Yeah. You have a comment, Sten Cato? Yeah.
We need to find a good economical and sustainable solution because we have 1 million electrical cars and 9 out of 10 new cars sold are electric. So we have to work with this to find the best solution.
Yeah. And we had also a pretty severe case actually last year where there were loads of used EV batteries stored in this very unsecure location, and nobody really wanted to take responsibility for it. So that's yeah, but it's really interesting to see how we have very different perspectives because we have different sort of levels of implementation of batteries. So obviously, like economy, so public perception, that's one important part, but also the economic perspective, as we've also heard several presentations pointing out here, and we've looked a lot at the numbers. And since we also see now that, of course, second life batteries, the price of new batteries have really dropped a lot, like very quickly, because batteries coming from China are so cheap that second life batteries it's really difficult for them to compete. But is there, as an end user, is there any way that we can kind of incentivize end users to choose second life over first life batteries? Any thoughts of that? Can we use, for instance, the carbon footprint or?
Of course, the environmental issues are a key driver for some of the consumers, but I think that for quite many of them, the price is still the main driver. So we need to, of course, focus on that, or then by regulation, of course, drive the development into that direction, that the second life of the batteries would be a more feasible option in the forthcoming years than it nowadays is.
Yeah. So I know at least some of the public authorities that SINTEF has worked with in Norway, they're very concerned with, they can kind of say that, okay, we can implement a little bit more expensive solution if show that it has a much lower carbon footprint. Is that something that, for instance, in Østfold, is something that you could go for, or is that still, is price still the main factor?
For end users, I think price, of course, is the most important, and how steady the system works. We have Enova, Norway's National Energy Support Agency, have supported some project in Trondheim, your hometown.
Yep.
Tiller School. So, but the support schemes are often aimed at innovation and not scaling. And I think for incentives of certification schemes such as BREEAM, there are no positivity by choosing second life batteries either, I think. So we can use a lot of incentive if we want.
Yeah, absolutely. But I think, yeah, so since we're really struggling to compete on price, and price seems to be quite important. If it comes to, so one challenge for Norway is that we are not part of the EU. I say challenge, I'm pro-EU. But that also means that the EU battery regulation isn't automatically adopted in Norway. The EU battery regulation came in 2023, August 2023. They are working on a Norwegian version of it, but it's still not active. It takes time. But is there, do you think, I mean, I realize you probably are not experts in the battery regulation, but do you think that it could make a big difference in the long run? Or do you have any feel for how the EU battery regulation could help or even hinder acceleration of second life BESS?
Well, I think that in the long run, I think it will be pro second life use, because we get more data from the batteries. You can like trace their lifespan and also like follow the life cycle of the battery cells, and like then also choose the cells that are like usable for the second life, and then we get more experience, of course, also from the second life solutions. I think that in the long run, then the end users will probably take them more into action based on the traceability and visibility on the data and history on the batteries and how they can be utilized prior to the material recycling phase in other ways.
Noah?
Yes, I would agree to this point, and I would like to add a little bit more that, of course, the regulations will certainly help. The data availability will help, but not until we make a strong business case for it. As such as the costs are very high, it's very difficult to make a market. But of course, if we have the data and the history of the battery, then we can maybe eliminate some of the extended testing of these battery, and this will reduce the cost. So for end users, the most important thing is return over investment. What's the payback period? How much savings can we get? So as long as we cannot give them this straight answer or a very good answer that they want to hear, it's very difficult to convince people just on sustainability thing.
Yeah. No, I think you're right. It's a challenge, but hopefully we'll see more second life eventually. I see we're running a bit out of time, and we need to get back to the plenary session eventually. But maybe if you can have like a last from each of you, just kind of like a last thought on what's the prospect in your different regions. What do you think it takes to kind of get more batteries and more second life batteries? Sten Cato?
I think second life batteries don't scale on belief, they scale on incentives.
Very good. Concreted very points. Noman?
The final thing, not until we reduce uncertainty and of course the revenue stream, we have to define it, and of course build trust of people in batteries, and especially in second life batteries. Then this will work. So we need not something like a policy driven approach, but rather we need a market driven approach. Then it will work much better.
Yeah. Pirkko?
Yes, I pretty much agree with what you said. And of course, as I mentioned earlier, the market-driven approach is already working quite well. And I think that when we get more experience and from these kind of systems, whether they are second life or first life, preferably second life solutions, of course, the more I think the end users will approve and utilize these kind of opportunities. And of course, the data and the safety issues, like the technical trust on the systems that they will operate and they are safe, is very important, and how to build that. And also, of course, the commercial aspect, that what kind of time, that kind of things. And also the liability is very important, that if something happens, and because we don't have that kind of systems ready yet, that what is the model. I think when we get also that in place, that will then boost the second life utilization.
Great. Thank you very much for your valuable insights. And I think it's safe to say that both second life batteries, but maybe even like stationary batteries in general, are technology is a bit ahead of the legislation and the standards. So we need to kind of catch up to get this going, really. But I think in the interest of time, I will thank all the speakers and the panelists. I think this has been a very insightful afternoon, and give a big hand of applause to everyone. Thank you very much for everyone being here, and we will all meet back, and we have 10 minutes to get back up to the 8th floor. So thank you so much.
Thank you.